Good morning, good afternoon, good evening guys, gals and gentlebuds, and welcome back to the shed. We are in the shed because today we're going to make a start on doing some work for the engine. Now I know I've mentioned building the engine, but I've got to do some prep work before I start putting it together. I've done the prep work on the block, remachining the back end, the oil pickup, etc., which I've detailed in a previous video. So today I'm going to make a start on porting the cylinder head, which is something that was supposedly done to this cylinder head. It was supposed to have been lightly ported, but when I pulled it apart it hasn't seen a grindstone since it left BMC Christ knows how many years ago. So that's got to be done. I can't just go in willy-nilly. I need to be able to measure the improvement in airflow from the porting work. So to that end I've built a very basic Flowbench. I haven't got the facilities, the space, the time or the enthusiasm to go the full hog, so I've got a very basic system set up which I'll show you shortly. I've also decided to lighten and balance the con rods. I know in an earlier video I said I wasn't sure whether to bother or not. The original rods were a pile of crap, so they went in the fuck it bucket. So I got another set of rods off eBay which are in good condition, but they're stock, so they need lightening and balancing. So that's basically what this video is going to be about. So I'll alter the camera angle and show you what I've got so far, and then we can get into it. Right, so there's my cylinder head. What I've created is a simple plenum that's connected to a vacuum cleaner, and these trumpets, if you like, they fit onto there, and they allow me to connect this, which is an anemometer. It measures wind speed, but by inputting the dimension of the air flowing through, so that the cross-sectional area of that, because all of the air will go through it, by programming that into this, it gives me a cubic feet per minute reading, so I can measure the airflow through the port, and then when I've modified the ports I can repeat the test and compare and see if I've made an improvement. So that one does the two end exhaust ports, that one and that one. That one does the central exhaust port, because this is a Siamese head, so cylinders 1 and 4 have their own individual exhaust ports. Cylinders 2 and 3 share an exhaust port, and cylinders 1 and 2 share an inlet port, and cylinders 2 and 3 share an inlet port. So hence it's a 5-port head, and that trumpet does the inlets. So on the top of the cylinder head, if I just tip that up for you, oh, before I do, so that's the exhaust manifold gasket. I've just checked, and this is a good match to the exhaust manifold on the ports. So as we can see, there is quite a significant difference in cross-sectional area between the gasket, and therefore the exhaust manifold, and the port in the cylinder head. I mean, in places there's got to be 5mm of metal that can be removed, increasing the cross-sectional area of that port, and hopefully therefore the airflow. The centre exhaust port is similar, and this one is similar. The inlet ports are a pretty close match, and they actually have a guide ring that fits into there to locate the manifold. Right, so this is the test setup. I've got my cone mounted on the inlet ports for 1 and 2. I've got the vacuum cleaner connected, I've got my airflow meter hooked up, and I've got M6 bolts to open the valves. So if I do, they're M6 by 1mm pitch on the thread, therefore if I do a quarter of a turn at a time, that's 0.25 of a millimetre, or 10,000ths of an inch approximately. Right, at 1/4 I'm going with 9. Right, so cylinders 1 and 2, there's a few discrepancies, probably down to the inaccuracy of a relatively cheap meter, but it gives me an idea of the airflow. When I get to 6.25mm of lift, from there on I'm getting no increase in airflow. So I'll move this onto the inlet port for 3 and 4 and we'll check them. It's never going to be as accurate as a full bore proper Flowbench, but as long as I can get some meaningful readings as a comparison before and after, then we should be good to go. Right, let's do number 3, which is that one. That's the inlet port. Right. Right, well, that's all 4 inlets checked, and there is some variation, but that could be down to the inaccuracy of a cheap meter, and I'm trying to take an average reading. I don't know whether I'd be better off taking a maximum reading, because we're getting a bit of fluctuation in the readings, which could be down to voltage fluctuation on the mains power supply. But overall they're all reasonably close throughout the range. Some points in the range like 2.75 millimeters of lift, we've got 75 cubic feet per minute on 1, 74 on 2, 74 on 3, 74 on 4, so they are very close. At 3mm of lift, 76, 76, 76, 77. Right, I'll get set up and we'll do the same for the exhausts and see what kind of flow rates we get on those. Right, I'm set up, got my flow meter, put that onto the cone. This is the exhaust cone for cylinders 1 and 4. So I've got that on and I've set it the right way for air going that way. I've changed the air hose on the vacuum cleaner to blow. So let's get to it. Right, so that's cylinder 1 done for the exhaust. Now the figures are quite a bit lower than the inlet, and that's not really a big surprise because A, the exhaust port is smaller, the exhaust valve is smaller, and we're blowing rather than sucking. But what you've got to bear in mind is that when the engine's running, as the exhaust port opens, the exhaust gases are pushed out under high pressure. There's several hundred pounds per square inch of pressure in the cylinder to start with. That's what's pushed the piston down, and then as the piston starts to come back up on the exhaust stroke, it applies pressure to the exhaust gases and pushes them out of the exhaust port. So while the figures I've got there are quite a bit lower than the inlet port, in fact about 50% lower, that doesn't really surprise me. But it does suggest that there is a fair bit of gain to be had in the exhaust ports. I'll see what the others do. I'll do cylinder 4 now, simply because I've got the flow meter set up on this cone which does cylinders 1 and 4. And all I'm doing when I start off, all I'm doing is I'm watching the fan in the sensor unit, and as I gradually open the valve, once I see that blade just start to move, I'm taking that as my 0 point. Yeah, that's just cracked. Right, those figures are a little disconcerting. The initial opening, the first quarter of a millimetre, was very similar, but at half a millimetre opening I got twice the airflow as cylinder 1. At 3/4 of a millimetre I got 2.5 times the airflow. At 1 millimetre I got nearly 3 times the airflow. So either the readings I took were inaccurate on cylinder 1 for some reason, or cylinder 1 exhaust port is absolutely terrible. But I think I'm going to switch this back to cylinder 1 and redo the test on cylinder 1 and see what we get, because that is a massive discrepancy. Right, let's try again. Right, I repeated the test on cylinder 1 up to 3 millimeters of lift, and I'm getting exactly the same figures, well, as near as, damn it, 5, 5, 9, 9, 12, 11, 13, 13, 18, 15, 20, 20, 23, 23, 25, 25, 26, 26, etc, etc, etc. So it looks like cylinder 1's exhaust port is pretty shocking. Right, So now we need to move that, tape that in place. And away we go. Cylinder 2 starts off slightly worse than cylinder 1, up to the first half millimetre, but by 3/4 of a millimetre it's gained 6 cubic feet per minute over cylinder 1. Although that's still 10 cubic feet per minute short of cylinder 4. So let's see what cylinder 3 does. If I can just get all 4 cylinders to flow all the inlets pretty evenly and the exhausts pretty evenly, but if I can improve the airflow so it will flow more cubic feet per minute, it should improve the performance. It's got to improve the performance. Right, let's see what cylinder 3 does. Basically the exhausts are all over the shop. I knew they were never going to be great, being Siamese ports on 2 and 3, and the port shaping on 1 and 4 isn't great, but even so I wasn't expecting that level of variation. I mean, just to pick a couple of spots in the range, at 2mm of lift, cylinder 1 25, cylinder 2 35, cylinder 3 29, cylinder 4 44. That's a huge variation. 4mm, cylinder 1 31, 2 47, 3 43, 4 68. They all seem to level out from about 5.5mm, give or take. Right. Well, I think what I need to do is chart all of those figures as a graph, and then I can see better what I've got. So we'll go indoors and do that. Catch you in a bit. Right, I'm back in the room. Right, after a bit of faffing about because I had difficulty with computers, I've managed to plot a graph of the airflow, and as you can see, cylinders 1, 2, 3 and 4 are all pretty even. Nice steady curve, that's all okay. The exhausts are a completely different matter. So there's all the charted information. The graph, as you can see, the airflow properties of the exhaust ports are all over the shop. So obviously from that we can take it that the exhaust ports need more work than the inlets. The inlets will be receiving some work, but I think the majority of the gains are to be had in, first of all, matching the exhaust port flows. Cylinder 1 is that blue line, cylinder 2 is the red line, cylinder 3 is the green line, which is abysmal, and cylinder 4 is this purpley coloured line, which is the best one. So you can see that. So there we have it. Right, so the next stage will be to get the cylinder head off the Flowbench, pop the valves out and have a look and see. First of all, need to establish where the restrictions are in the ports. That's the first and foremost step. You don't just want to go in willy-nilly with a grinder and start cutting material away, because if you're taking material away from the wrong place, it won't do any good at all. You need to take the material away from the places of maximum restriction. So all of that kind of information is in David Vizard's book, and there are cross sections of cylinder heads, ports, to show you where to take material away and what the desired port shape is. So there we have it. Let's get this head off and pop the valves out and have a look and see what we're up against. Right, so let's get all the valves out, turn the head up the other way, and so we're looking into cylinders 2 and 3 now. This is cylinder 2, this one's cylinder 3. That's the inlet port and that's the exhaust port. And as you may be able to see, the inlet port is quite a lot deeper than the exhaust port. So the throating, if you like, on the exhaust port is pretty horrendous by comparison to the inlet port, and the inlet ports ain't great. Also, you can possibly see there, just in there, see if I can get something to point it out. So that there is where the port has been machined to, and there's a step. No such machining on the exhaust port is evident, but then it has got a bit of carbon build-up. And the same in cylinder 3. In fact, in cylinder 3, that step is really quite big. Now what that will do is cause turbulence in the airflow, along with that step there, that ridge around the valve guide. So that needs blending down along all 4. I can't see anything obvious in cylinder 1 exhaust port to make it so much notably worse than the others. I will eventually be cleaning up the combustion chamber faces. Once I've got the ports matched and airflow improved, I will then be cleaning up this surface, and I think there is a bit of reshaping that can be done in the combustion chamber. Get rid of this rough surface and these steps, because they won't help airflow. The exhaust valves, well, both the inlet and the exhaust valves are actually quite heavily shrouded by the edge of the combustion chamber, which doesn't help airflow. There's not a great deal you can do. I mean, we can cut a little bit of material away around these edges, but not a massive amount. So they're always going to be shrouded to some level in that area. We can open up that side a bit. What I don't want to do is take out too much material out of the combustion chambers and lose the gains in compression ratio that I get from the flat top pistons. So it's all a bit of a balancing act. First thing to do is get the ports machined up, get the ports cleaned up, see if we can improve some airflow, and then get the valves back in, test it again on the Flowbench to see what we're doing, see what gains we've got, and then I can measure accurately the volumes of each combustion chamber, calculate the compression ratio, and then I will know how much material I can afford to take out of each combustion chamber without losing too much compression. There's a lot of work involved, just a lot of hours of work involved in cleaning the head up. Right, so I think that's about it for this video. Hopefully you found it interesting. If you think I've made some mistakes, by all means feel free to pass the comment. I'm learning as I go. This is stuff I've not done before. The Flowbench is a crude, I won't say bodge up, but it's a crude device that I've built to enable me to measure airflow. Now it's not going to be as accurate as a full-blown superflow or something like that, I only need to be able to measure airflow and before and after and get a comparison. So it's a simple comparator device, if you like. Anyway, enough of that nonsense. Hopefully you found it interesting. If you do, hit the like and the subscribe and the notifications, and the next video I'll be getting busy with the grinder on this head, and I'll see you then. Thanks for watching.